Okay, so let me start recording. All right, welcome everyone to Harvard CMSA Quantum Matter in Math Physics seminar series. We are very happy to have Carolyn Zhang from Chicago. Carolyn currently is finishing his PhD supervised by Michael Lavin, and she has done many interesting work such as deconfine quantum criticality, exact soluble model, and for K phases. She will be speaking about her recent work with Clay Cordova on anomalies of 1+1D categorical symmetries. I should also mention that Carolyn will be graduate from Chicago and join Harvard as a junior fellow this year. So we will anticipate more interaction with Carolyn. And let me remind the audience, please feel free to ask questions and interact with Carolyn during her talk. And let us welcome Carolyn. Please, it's all yours. Thank you.
Okay, thanks, Juven, for the introduction. And yeah, please interrupt with questions. I'm happy to have this opportunity to talk about this paper that I put out with Clay about a month ago on anomalies of 1+1D categorical symmetries. So the outline for today is I'll first set up the problem. The problem is basically how to detect when a fusion category symmetry is anomalous, and I'll tell you what exactly I mean by anomalous in this context. And then I'll tell you the solution that we came up with. And the solution is that a fusion category symmetry is anomaly-free or is anomalous if there's an obstruction to the existence of an object called the magnetic Lagrangian algebra of the bulk topological order, which is the Drinfeld center of this fusion category. And I'll get into what exactly that means later. And then we can apply this approach to study anomalies of Zn times Zn Tambara-Yamagami fusion categories, which I'll also define as we go on. Okay, so let me first define what I mean by anomaly. So let's define what I mean by anomaly. So I'm going to define anomaly as an obstruction to flowing to a trivially gap phase. By trivially gap, I mean that your system is symmetric and the ground state degeneracy, so the ground state degeneracy is equal to 1 on any manifold. And this is because we know that to Hooft anomalies, which they're the focus of this work, they're invariants of RG flow, and the trivially gap phase certainly has no anomaly. And so then we define anomaly as an obstruction to flowing to this trivially gap phase. So if it's anomaly-free, it can flow to this trivially gap phase. And this is so an example of these kinds of anomalies that are very familiar to many of you are anomalies of a unitary symmetry. Unitary symmetry group G. And these, and if you're looking in D+1 dimensions, so D is the space and 1 is for time. For D+1 dimensions, these are classified by this D+2 cohomology class. And I'm going to focus on 1+1D for the rest of this talk. So let's just assert that we're going to look at 1+1D. And an example of such a 't Hooft anomaly is when we take G equals Z2. So in this case, if you evaluate this third cohomology class, you'll find that gives you Z2. So there's basically an anomalous Z2 symmetry and a non-anomalous Z2 symmetry. The anomaly-free one, if you can write it very explicitly. So if you have a 1D spin chain of qubits, then you can write the anomaly-free realization of the symmetry in the following way. And you can write the anomalous realization of the symmetry in this non-on-site way. And so these are two realizations of the symmetry in 1 plus 1D. You can show that this one is anomaly-free because you can write down a Hamiltonian whose ground state respects the symmetry and it has a unique ground state. And for this one, you can show that that's not possible. You can't have a 1 plus 1D theory that respects the symmetry, has a unique ground state, it's gapped. So this is anomalous. And this was discussed in Love and Gu, 2012. You can also study this from a lattice perspective, from a field theory perspective. You can write down a compact boson field theory and write down how the symmetry is acting. You can show that there's an anomalous realization of a Z2 symmetry and a non-anomalous Z2 realization of the symmetry. And then the question is, given this kind of symmetry, how do you detect whether or not it's anomalous? For this kind of symmetry, the anomaly is given by this the F symbol, which tells you about how the domain walls fuse. So the F symbol looks like this. This is going to be elements of your group. And what you can show is that for this anomaly-free one, you have F of X, X, X equals 1. This X is a non-trivial element of Z2. And for this anomalous one, you have F, X, X, X equals -1. This F symbol tells you about how the domain walls fuse. And therefore, it's a map from G times G times G to U1. Because the domain walls fuse associatively, but only up to a phase. And there's a kind of a condition that this F symbol has to satisfy, a consistency condition, which is the pentagon equation. Given here, this is basically a cocycle condition because this tells you that F equals FFF. So you have like FF equals FFF. That's a cocycle condition. And this F symbol is trivial if it's a 3 co-boundary. So what that means is you have, this is equal to, as I mentioned, F A, B, C times this. And what the idea of 1 is trivial is basically if you can write this U1 phase, you can decompose it into these little vertices here. So upon a redefinition of the vertices, you can get rid of this phase. So that means that F A, B, C is equal to beta A, B. That's this phase here, times beta A, B, C over F beta A, B, C, beta B, C. So when the F symbol takes this form, then you can just redefine these vertices and get rid of the F symbol. And so then you don't have this anomalous phase. But if you can't get rid of the F symbol by redefining the vertices with these phases, then this F symbol can't be removed. And so when you try to proliferate domain walls in your system to try to get a unique symmetric gap phase, then you get inconsistencies and ambiguities due to this F symbol. Okay, so now we understand. So if this F symbol is a non-trivial 3 cocycle, then there's an anomaly, you can't remove this phase. And so in particular, that happens in this case. And in fact, you can compute this F symbol explicitly from these symmetry operators. There's a couple of methods. One is else, and Nyack back in 2014. And another one is Kawagoe and Levin, 2021. Okay, so this is the story for our usual group-like symmetries. We know when there's an anomaly. And the question is, how does this extend to fusion category symmetry? So let me first give you a definition of fusion category. So fusion category, so this is going to be a global symmetry of 1 plus 1D systems. This is fusion category, which I'm going to label by A, this curly A. There are a couple pieces of data that go into defining a fusion category. So the first is the simple objects. If you just have an ordinary group-like symmetry, then the simple objects are just going to be the elements of your group. But in general, they can be more complicated. The second piece of data are the fusion rules. These are given by these kinds of fusion coefficients. So you have A times B is sum over C, and A, B, C, C. So in the abelian case, you only have one element on the right-hand side, but in general, you can have a sum over elements. This is familiar from if you're looking at representations of a group, you can have a tensor product of two representations A and B that give you a direct sum of lower dimensional representations. The fusion rules give rise to something called the quantum dimension that you can associate with every simple object. dA, which satisfies dA dB equals sum over C and A, B, C, DC. And that just looks like this diagram. This is your A line. And of course, you don't want to consider any kind of non-invertible object. You want some additional structure. So for example, you want this to contain the identity element. And you also want for every A in your fusion category, you want there to exist a unique A bar, which is the kind of antiparticle, such that their fusion product includes the identity element. Okay, so this is our fusion rules. And then the third and final piece of data is the F symbol, which tells you about associativity of the fusion. And now, because you can have two objects fuse into multiple different objects, but you instead get the F symbol is no longer valued as a U1 phase. So this is A, B, C, D, E. And this is going to be a sum over F. A, B, C. Let me move this here. D, F. This is going to be F, A, B, C, D. And you need these indices E, F, because you can have multiple fusion channels E and F. Okay, so this defines your fusion category. One example of a fusion category that many of you are familiar with is the Ising fusion category, which has this simple objects 1 sigma. F is like your Z2 symmetry, and sigma is a duality symmetry. This is a symmetry of the Ising 1 plus 1D quantum Ising model at its critical point because it's invariant under the Kramers-Vannier duality. And the fusion rules are given by as follows. And then F times sigma equals sigma, and sigma times sigma equals 1 plus F. The idea is that basically doing this Kramers-Vannier duality twice projects you into the symmetry even sector. And then what you also have is the F symbol. So a lot of the F symbols are trivial, but for example, these F symbols are non-trivial. F1 equals minus F sigma, 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 F. Those Frobenius-Schur indicator over square root of 2. So this Frobenius-Schur indicator is plus or minus 1. It's called the FS indicator. And it will come up later as well. But this is just an example of a fusion category. And there are many fusion categories, and they realize symmetries of lots of different kinds of systems. So for example, in CFTs, there's fusion category symmetries, and these anion 1 plus 1D anion chains, there's also fusion category symmetries. And there's also people constructing tensor networks, matrix product states that have fusion category symmetries. And as we will see, there are also gap bases that have fusion category symmetries. So they're pretty ubiquitous, and we would like to understand them. In particular, we would like to understand when they are anomalous. So that is the main question. So that's our question. So given all of the data that specifies A, how do we know whether or not it's anomalous? And this, at least to me, it wasn't obvious at first because this F symbol isn't even valued in U1, it's some tensor. And so there isn't really a obvious generalization of the cocycle condition. So given this F symbol, given all the fusion rules and the simple objects, how do we know whether or not this fusion category symmetry is anomalous? That's the question we would like to answer. And there's two approaches to how to answer this question. One of them is one that's already known in the literature, and then the approach I'll talk to you about today is our approach. So there's an edge approach. This edge approach, I'm calling it an edge approach because it only kind of uses data of the 1 plus 1D theory. So I'm thinking about the edge of the topological order in one higher dimension, which I'll mention later. But this is one approach. It's an edge approach. And what it says is this fusion category is anomaly-free, free if and only if there exists something called a Fiberfunctor. This is a functor from your fusion category A, the category of vector spaces. This is a category that has only one simple object. And each Fiberfunctor defines a 1 plus 1D SPT plus 1D ASPT of this fusion category symmetry A. I can say more about what a Fiberfunctor is, but because that won't be the focus of this talk, I will just say that this mathematical object exists. And so then the question is, you have this fusion category symmetry and you have to search for a Fiberfunctor. If you can't find a Fiberfunctor, then you know that the fusion category symmetry is anomalous. This method is a little bit overkill because it doesn't only tell you whether or not your fusion category symmetry is anomalous, it specifies all of the data that tells you, that enumerates the 1 plus 1D SPTs of this fusion category symmetry. And in general, it's it's difficult to go about trying to find a Fiberfunctor. So this is kind of a difficult task. And so let me tell you, yes.
Okay, yeah, several questions. Let me just make sure. Yeah, maybe since you mentioned this Fiberfunctor, is that also only for the 1 plus 1D anomaly? So which dimension of this anomalies?
Yeah, we're gonna only be looking at 1 plus 1D in this work.
Okay. But in the Fiberfunctor defines some 1 plus 1D SPT.
Yes.
Not 2 plus 1D.
No. Because the symmetry is anomaly-free if you can have a SPT of the symmetry, right? In 1 plus 1D. So if there exists a Fiberfunctor that defines your anomaly-free theory, which is a 1 plus 1D SPT of the symmetry. If it defines for you a 2 plus 1D SPT, then if you can only realize that they're at the boundary of a 2 plus 1D SPT, then that means it's anomalous, right? So what you want to find is a 1 plus 1D SPT.
Okay.
Okay. And so let me just write some references for this Fiberfunctor method. For the experts, yeah, okay. If you're an expert, you probably already know what it is, but it's basic. Yeah, I can. If you're curious, I can say more words, but you can look at these references. This is the tensor categories book. Okay.
Sorry, let me ask.
Yes.
Yeah, there's a few things. Sorry for that, but actually, let me ask something earlier. You try to write down this 3 cycle, right? Maybe you write omega or alpha. I forget. Let's see. The 3 cycle, and then you say that if it's not if it's a 3 boundary, you will split it into lower dimensional 2 chain. There's some co-cycle condition analogy for that when the fusion obey group law, right? Earlier in your, just maybe you can go up a bit. Let's see. I just want to see how do you think about this condition based on maybe this F symbol point of view? Well, certainly from the co-cycle point of view, it's like you put a 3 co-cycle on some 3 simplex, and this evaluation of that somehow become just evaluate products of a 2 co-chain put on the 2 simplex, and yeah, and this will be the way to like interpret this in terms of the usual co-cycles assigned on some simplicial complex. But here, I guess you are trying to say something about the point of view you are taking from the F symbol. I just want to make sure I didn't miss some information here. Is there something you want to clarify that?
Yeah, I'm not sure if I have anything more to clarify about this. It's just saying that you can add local counter terms to get rid of the F symbol if it takes this form.
Okay.
Was there like a specific question, or?
I can get this anyway, but that's fine. Yeah, thanks. I just want to make sure you have more to aid. Okay. I see. No problem. Another question, Zach. Suppose I have this maybe anomalies within some symmetry G, a group. Is there some example that you may know that maybe that anomalies it has anomaly in G, but perhaps it become anomaly-free in some category symmetry instead of G become something like this A mass scale A. Do you know any such example?
Well,
Do you know what I mean?
I mean, if you already have an anomalous like group, then like, for example, in the normal group-like case, if you already have an anomalous subgroup, then certainly the whole group is anomalous, right? Like if you already have an anomalous subgroup, like a Z2 cross Z2 symmetry, and one of the Z2s is anomalous, then of course the whole group is also anomalous. So in that sense, I wouldn't expect that to occur. What we will see is that you have something interesting where like you have a Z2 symmetry that you think might be anomalous, but the way it plays into this fusion category symmetry makes it actually not anomalous. But I think that's a bit different from what you're saying, but that's a kind of a flavor of maybe is related to what you're saying. Yeah. But I can say that when we get into the example.
Right. Yeah, let me just make the statement. I think there should be some example, like I view this way of thinking, it seems like you have a maybe anomaly, 1 plus 1D anomaly, perhaps in G, and you might require some 2 plus 1D GSPT. Perhaps you are trying to oversolve this 2 plus 1D GSPT to a 1 plus 1D, this A, maybe categorical version of that SPT. Is there some kind of things you are doing here like that?
No, in general, a fusion category doesn't have anything to do with a group. So we're just starting from a fusion category.
Yeah, no problem. Yeah, okay. but I suppose what I say still makes sense, and I can clarify that later. But thanks.
Yeah, but actually the ones we'll look at are related to groups, and so there's
Yeah, what I try to say is maybe in one simple sentence is categorical version of symmetry extension, trivialization or anomaly. Yeah, but anyway, I can mention that later. Thanks.
Okay. Okay, so let's talk about the approach. Sorry?
So A is anomaly-free if there exists a Fiberfunctor. Can there exist multiple of them?
Yeah, so then if there exist multiple Fiberfunctors, then that means that there are multiple 1 plus 1 DSPTs of the fusion category symmetry.
I see. Thanks.
Yeah. Okay, so this is the approach that we're going to take. This is kind of a bulk approach where we use the topological order in one higher dimension. So what we say is this A is anomaly-free, free if and only if there exists something called a magnetic Lagrangian algebra of the center of A, the Drinfeld center of A. This is also, so this is called the magnetic Lagrangian algebra. The center of A is also called what people have been calling the symmetry TFT. Or the string net model, the Drinfeld center, Trivero theory, whatever you want to call it. And this is, so you can, this has been discussed in Kong et al. 2020 and Reed, Moore, Telemann, Telemann, 2022. And also, let me give one more reference, Katie, Omori, Zhang, 2022. Okay, so this is a topological order in one higher dimension. And what we can do is this topological order has certain gap boundaries that are labeled by these Lagrangian algebras. And what you're looking for is a certain kind of Lagrangian algebra. So let me give you some intuition for what this means. So in any topological order, so let's look at some topological order. And this is going to be the bulk. So this is going to be, this is the center of A. And as I mentioned, okay, so you can think of this as actually wrapping a cylinder. So this is like the cylinder. You can think of this going around the other side. And you can label the gap boundaries, as I mentioned, by Lagrangian algebras. So I'm going to have this purple thing is going to correspond to something called the electric Lagrangian algebra. So whenever you have the Drinfeld center of a fusion category, this electric Lagrangian algebra is a gap boundary that's a given. So it always exists. And the electric Lagrangian algebra, so for example, in tort code, the electric Lagrangian algebra would describe, say, the rough boundary where you can condense the E's. And so this is a boundary in which the E can just kind of be pulled in and disappears. So whenever you have a gap boundary that defines a fusion category, which defines the low energy excitations that are like domain walls. So in the toroid code case, that's because the M's, when you pull them to the boundary, they get confined. And so they act like so then in the edge theory, they act as Z2 domain walls. So what you can imagine is you can imagine nucleating two of these Z2 domain walls and wrapping them around the cylinder. And that gives you a fusion category because the elements of these domain walls, they multiply, they fuse to form a fusion category that's precisely the same fusion category A. That's kind of by definition that the low energy excitations at this electric Lagrangian algebra form a fusion category A. And now what you can do, so now let's consider having this LE boundary condition. This is also Dirichlet boundary condition when you have some G gauge theory. So we can have Dirichlet boundary conditions on both sides. So this LE is on both sides. And now what we're going to do is we're going to kind of shrink this system. So now we have effectively like a 1 plus 1D theory. And again, we're going to have this LE on both sides. And this boundary condition, as I mentioned, it means that you can have E's that are absorbed into boundary. And because you have LE on both sides, you can also have E that tunnel across, right? Because it can be absorbed by both sides. So this is E. And so now what you have is you have now effectively a 1 plus 1D theory. And you have this fusion category symmetry A. And this fusion category symmetry is spontaneously broken because you have operators, these local operators that are charged under the symmetry that gain an expectation value because this E can tunnel from one end to the other. Okay, so this defines a 1 plus 1D theory that completely spontaneously breaks your fusion category symmetry. because you have all of these charged operators that gain an expectation value because they can tunnel from one side to the other. Okay, so now let's consider a similar setting. So we have our topological order in the bulk. This is going to be our center of Z of A. And now what we're going to consider is, again, we're going to put this Dirichlet boundary condition on one side. So this is our LE. And this defines for us a fusion category symmetry A, again. But now what we're going to do is we're going to have a different boundary condition on the other side. So now we're going to have this different boundary condition, which is defined by the other Lagrangian algebra, which I'm calling LM. Okay. So now you have this setting, and what we can do is we can do the same thing as before. So we're going to shrink this cylinder. So now it becomes effectively a 1 plus 1D theory. And again, we have this magnetic boundary and we have this electric boundary. But now we have this fusion category symmetry, A. So this is, we still have this A, but now it's no longer spontaneously broken. And the reason why it's not spontaneously broken is in this setting, you can still have the E go around and come back to the same boundary, but you can no longer have the E tunnel from one end to the other, because the other one, what I'm going to show is that this magnetic Lagrangian algebra, it defines a boundary in which none of the anyons in this electric one can actually terminate. In other words, what we're going to use is LE intersect with LM is equal to the identity. This is very important and kind of the defining feature of this other boundary. So because they intersect only on the vacuum, that means that you can't have this E tunnel from one end to the other. So that's not allowed. And so that means that now you still have a 1 plus 1D theory that has a fusion category symmetry, but it's not spontaneously broken. And now by construction, whenever you have this LM, then that gives you a 1 plus 1D theory that is an SBT of the fusion category symmetry because it's not spontaneously broken. This theory will have a unique ground state on any manifold. Okay, so in conclusion, what we have is each of these magnetic ones specifies a 1 plus 1D ASBT. So in general, it's very difficult to find a magnetic Lagrangian algebra. In fact, it's pretty much just as difficult as finding a Fiberfunctor. But this is pretty intuitive, and there are obstructions to finding a magnetic Lagrangian algebra that you can get without specifying the full one. So for example, one thing that we will use a lot is in order for you to have a magnetic Lagrangian algebra, you need enough bosons in your Z of A, in your topological order. So when there doesn't exist enough bosons, you can already rule out that this object exists without trying to find all of the data that defines this Lagrangian algebra. So then what we will find is somewhat easy obstructions to compute. Yes.
So just double check. So even when A is not a fusion category, even A just a group, this condition still work, right?
Mm-hmm.
For example, if we take A just a Z2.
Yes, we will go through all of the detail of the Z2 example in a moment.
Okay.
Yes.
Like torical and double semio, then that double semio version of that will be anomalous, but torical,
yes.
You have E and M.
Yes.
But I want to ask whether the case, if you have an E or M, is that notion for M is unique? Probably not necessary, or it will be unique.
Yeah, so it's not like what all we'll do is use the fact that the anyons in this LE and the anyons in LM intersect trivially. Of course, there are like multiple M's, which is why you can have multiple different SBTs.
Okay.
Yes, which we'll go through in an example. Like for example, if you take any M and you attach an E to it, then it's also another M. So yeah, you can have multiple LMs, but you have a unique LE that's specified by your fusion category.
Okay.
Okay. Okay. So
yes. Sorry. The notion of M here is not quite magnetic, or is that really, why do we call this M? Like, if there are multiple possibility, I just wonder, say maybe this can be just a requirement for another Lagrangian subgroup of something else, not necessarily M. Because
Yeah,
from
I mean, it's just a Lagrangian it's just a Lagrangian algebra that intersects trivially with this canonically defined one. I'm just calling it LM because I initially thought of it from the Z2 gauge theory perspective, but yeah.
could be
Okay.
something like E prime, E bar, or something. Anyway.
Yeah, you can call it another name if you want to, but this is just a definition.
Okay.
Okay. So why would you so this is our bulk approach, and this is important, so I'm gonna box this. And why would you want to use this approach? Well, as I mentioned, one reason is they can give you easier to compute obstructions. You don't need to specify the entire Lagrangian algebra. You can probably also do that with the Fiberfunctor, but it's not obvious. Another reason why you want to use this approach, so that makes it easier to detect anomalies in some cases. Another reason why you might want to use this approach is just because Lagrangian algebras are much more familiar to condensed matter theorists. At least it was more familiar to me. So it's a more familiar physical object to work with. And I think it gives very complementary perspectives to the Fiberfunctor approach. But as I'll show, there are lots of cases in which you can pretty easily show that that the fusion category symmetry is anomalous from this Lagrangian algebra perspective, whereas in the Fiberfunctor perspective, it was much more non-trivial. Okay, so I've kind of hand-wavily defined these boundary conditions. Let me make the definition a little bit more precise. So let me define, so a Lagrangian algebra is kind of a non-simple object in your Drinfeld center. And it has these kind of integer coefficients. So these lie in the integers. And these are anyons in your Drinfeld center. And they satisfy a certain property, and dA equals D, where D is the total quantum dimension of your topological order. And so, as I mentioned before, you always have a canonically defined LE, which is Dirichlet boundary condition, if you have a gauge theory. And it's defined because if you have this LE on both sides, then you have a theory that and you squish it, then you get this theory that fully spontaneously breaks your fusion category symmetry. So as an example, if your fusion category is braided, then the Drinfeld center takes a very simple form. So if your fusion category is braided, then the Drinfeld center just takes this form. Oops. So it's just A stacked with A bar, the time reversal of A. And then in this case, the LE is just going to be equal to sum over A and A bar. And we'll give some other examples. So for example, in doubled Ising, this is just going to be 1 plus psi bar plus sigma bar. And now the question is, does there exist an LM? And the only condition, so this is kind of like Neumann boundary conditions. And the only condition that this LM needs to satisfy, well, in addition to it being a legitimate Lagrangian algebra, is that it intersects trivially with the electric one. So it only intersects on the vacuum anion. This is very important. Okay, so yes.
Yes, just make sure. But there are also some maybe generalized notion of some sort of anomalies that does not even allow gap boundary, right? Do those examples also should be included or considered? Is it, for example, I think we know that there are some like some fractional quantum Hall states, they can have a protected edge modes that cannot be gapped, and without symmetry protections, and does not even need to have a vanish chiral central charge, right? So are those
Yeah.
examples also, Lavin has a paper on that. I also have a paper on that, maybe with Xiaogang, and
Yes.
those examples count as some. Also, you may have some anomalies, but the condition of finding Lagrangian subgroup may not contain those cases.
Yeah, so specifically, that's a good point. I'm specifically looking at 't Hooft anomalies. So these are anomalies in the presence of a symmetry.
Yeah.
So in particular, of course, there are topological orders that don't have gap boundaries. But if you start off with a symmetry, if you start off with a fusion category and you take the Drinfeld center, then all Drinfeld centers have a gap boundary. So I'm only looking at kind of 't Hooft anomalies, of not gravitational anomalies or anything.
Yeah. Okay. Thank you very much.
Okay. Thank you for the question. Okay, so let's go through a very simple example, which is the example that Juven had mentioned. This is the example where you have this fusion category is VecZ2, and it comes equipped with some 3 cocycle. And so the simple objects in this fusion category are just 1 and x, where x is a non-trivial element of Z2. And they have abelian fusion, so you have x times x equals 1. Sorry for all the x's. And so because they have abelian fusion, then you can instead use Lagrangian subgroups instead of Lagrangian algebras. I'll define for you in a moment what I mean by Lagrangian subgroup. These are kind of easier objects to work with that you can use whenever your fusion is actually abelian. And then the third piece of data that we need to specify for our fusion category is the F symbol. So the F symbol is F of XXX. So whenever you have any other combination, then you can choose for it to be trivial. So this is going to be equal to this 3 cocycle. Oops. And there are 2 options. So it can be minus, let me put this 1 or minus 1. And I'm going to call the first one omega 0 and the second one omega 1. Okay, so this is going to be our fusion category. And now let me define for you what a Lagrangian subgroup is, because now it's simple enough to only use Lagrangian subgroups. So Lagrangian subgroups. So this is going to be a collection of anyons. So I'm going to put a tilde here because it's a Lagrangian subgroup, and the untilde ones will refer to Lagrangian algebras. So this Lagrangian subgroup is a subgroup of the anyons satisfying the following properties. First, you have theta AB. So the braiding statistics is equal to 1 for all AB in your Lagrangian subgroup. This just means that all the anyons in your Lagrangian subgroup braid trivially with each other, so they can be simultaneously condensed. The second property is that for all A not in your Lagrangian subgroup, there exists a B in your Lagrangian subgroup such that theta AB is not equal to 1. And what this means is that if your anyon is not in the Lagrangian subgroup, then it's confined. So basically half your anyons are simultaneously condensed, they're the ones in your Lagrangian subgroup, and the other half are braid non-trivially with elements in your Lagrangian subgroup, so they have to be confined. And so it follows also that the number of anyons in your Lagrangian subgroup is equal to the total quantum dimension, which is the square root of the number of anyons in your topological order. Okay, so now this is what we define by a Lagrangian subgroup. And we have 2 different topological orders because we have 2 different choices of omega. So this leads to 2 different symmetry TFTs. So if we take the center of VEC Z2 with omega 0, then this is going to be Z2 gauge theory, which is also the familiar torque code. And this anion theory, as we all know, it has 4 anions, 1 E, M, E, M, and you have 2 Lagrangian subgroups. So you have LE is 1E, and you have LM is 1M. And you can see that they intersect trivially. They only intersect on the vacuum anion. So this says that because this LM exists, this Z2 symmetry is anomaly-free. Now, if we take the center of vec Z2 with omega 1, this will be a doubled semion topological order, twisted Z2 gauge theory. And this also has 4 anions, so it has 1 S, maybe I'll do it in the same order. So 1 E, S, and ES. But now the problem is that the topological spin of S is I, and the topological spin of ES is minus I. So in particular, you only have 2 bosons, which are 1 and E. So all you really have is the electric Lagrangian subgroup, which is 1E. There is no magnetic one. There aren't enough bosons. And so now you can see that because there doesn't exist a magnetic Lagrangian subgroup, this symmetry is actually anomalous. And notice that we didn't even have to go through a search of Lagrangian subgroups. We already know that it's anomalous because there's only 2 bosons in this theory. And you need 2 Lagrangian subgroups that each have size 2 that intersect only on the identity. So you need 3 bosons, and this only has 2 bosons. And so, so it follows that there cannot possibly exist a magnetic Lagrangian subgroup. So this has to be an anomalous symmetry. Okay, so let's go through another very simple example. So example. Now we have Z2 cos Z2 gauge theory. This is just 2 copies of torque code.
Can I ask one question? I should ask earlier. I think that's a nice example. Thanks very much. A question about something you associate the maybe some Lagrangian subgroup with LE on 2 sides as spontaneous symmetry breaking. I'm not sure I get that point actually. Can you clarify what you mean there?
So in the torque code case, this just means that if you have rough boundary on both sides, then you have your M that becomes a confined kind of domain wall excitation on the boundary. And if you have rough boundary on both sides, then you can annihilate E on both sides. So now you have a charged operator under your Z2M symmetry, which is basically the domain wall, which is just the E string operator that creates an E excitation that tunnels E on both sides. So that anti-commutes with your Z2 symmetry. So it's a charged operator that gains an expectation value. That means it spontaneously breaks the fusion category symmetry.
Okay, but in the case of torical, it's break one phone Z2 electric symmetry.
No, it breaks so this is now a 1 plus 1D theory, right? So it's a global symmetry of your 1 plus 1D theory that's spontaneously broken. In this simple case, it can be roughly thought of as the M world line that gives you a 0 form symmetry. But in general, it's a bit more complicated. But in general, whenever you have a gap boundary that defines the fusion category symmetry, and then these E's that tunnel through are the charged operators that spontaneously indicate that there's a spontaneously broken.
Okay, so let's clarify. So spontaneous broken maybe from bulk or boundary, 2 plus 1D bulk or 1 plus 1D boundary point of view. Can you clarify what is broken? So I think the spontaneous broken of some symmetries, the condensation of the charge operator, right?
Mm-hmm.
And because now the electric line can go through between 2 boundary, maybe from the bulk point of view, should I what I'm not exactly sure, but I just try to say what I want to hear. Is that the one phone, this electric, this operator is the charge operator for one phone magnetic symmetry for the bulk,
Right, but now you've kind of squeezed it to be 1 plus 1D, so it's really kind of a local charge operator.
Okay, so that's broken of the these are the zero, sorry, what's the dimensional charge operator right now? It's a 0 dimension charge operators.
Yes, so this is now 1 plus 1D theory that has a zero form symmetry that's spontaneously broken.
And you will call this zero form electric symmetry or magnetic?
Magnetic symmetry.
Okay, good. Yeah, very, very good. Yeah,
Okay.
because E is a charge operator and the charge object is magnetic. Okay. Yeah. Okay. Thanks. Let me think of it. Thanks.
The symmetry broken, the symmetry that's spontaneously broken is the magnetic world line kind of.
Okay.
Okay, does that make sense or?
Yeah, it makes sense so far. Let me think more, but thanks.
Okay. Yes. It's a little bit confusing because you can't always, okay, maybe I won't get into the subtleties, but that's basically the story of what's going on there. Okay, so now another very simple example that we can go through is Z2 cos Z2 gauge theory. So this is just the anyons are generated by E1, M1, E2, and M2. And they both follow Z2 fusion rules. And then you can now have two magnetic Lagrangian subgroups. So this is going to be 1, M1, M2, M1, M2. This is one magnetic Lagrangian subgroup. And this is another magnetic Lagrangian subgroup. So this is 1, M1, E2, M2, E1, M1, M2, E1, E2. So you can see that both of these are collections of 4 anyons, because 4 is the total quantum dimension, and they're all bosons. They all mutually braid trivially. And so this says that in this theory, there are actually 2 magnetic Lagrangian subgroups, and that corresponds to the fact that in 1 plus 1D, there are 2 SPTs of Z2 cos Z2 symmetry, the trivial one and the cluster state. So this recovers the fact that the classification of 1 plus 1D Z2 cos Z2 SPTs is Z2. From your definition of Lagrangian subgroup seems to depend on the braiding information of the objects, but if I'm not mistaken, the total quantum dimension can be computed. Oh yeah, so it kind of follows from this definition that of Lagrangian subgroup, that if your topological order is of this form, which is the Drinfeld center of this fusion category, that half of your anyons will be confined and the other half is condensed. So then it will follow, if you look at all the anyons that can mutually braid trivially with each other, then it will just give you this condition. I'm not really defining, so yeah, I think that will just follow from the braiding from these two for this Lagrangian subgroup case. I was trying to respond to the chat question. Okay, cool. Okay, so now now we've seen 2 examples where we can see that the magnetic Lagrangian subgroups can tell you about the SPTs of the symmetry, but only in kind of the group-like case. So now let me tell you the general approach. This is our general approach. The first step is to construct the Drinfeld center. This is in general non-trivial, but there are a couple different approaches. For example, the string net construction. And then once you've constructed the Drinfeld center, what you can do is consider obstructions to the existence of a LM. And so that's our general approach. And what we can do is we can apply, application, we can apply this to Zn times Zn Tambara-Yamagami fusion categories, which I will define later. And these fusion categories I'm going to label them as Ty. So you can do it with any abelian group G, but we'll focus on Cn cross Cn, and a symmetric bicharacter and a Frobenius-Schur indicator. So these two define the F symbol. And this abelian group is part of the information that specifies diffusion. Oops. Okay. So for example, let me just tell you some of the non-trivial results that one can obtain. So when you take n equals 2, so Z2 cross Z2, Tambara-Yamagami, then you can show that this Tambara-Yamagami Z2 cross Z2 with a Frobenius-Schur indicator and bicharacter is anomalous. Oops. Anomalous for diagonal bicharacter and Frobenius-Schur indicator equals -1. But it's anomaly-free when you choose other bicharacters and for all other choices. So for example, you can have off-diagonal bicharacter, Frobenius-Schur indicator plus or -1, or diagonal with Frobenius-Schur indicator equals +1. The only one that's where it's anomalous is when you have this particular choice of bicharacter, the Frobenius-Schur indicator is -1. And the reason why it's anomalous is if you look at the Drinfeld center of this Tambara-Yamagami fusion category, there aren't enough bosons to form this magnetic Lagrangian algebra. In particular, there are certain bosons associated with a duality object, or certain anyons associated with duality objects, and none of them are bosonic, so that is obstruction. And we can also get many non-trivial results for Zn cross Zn, where n is greater than 2 as n, and n is odd, that I maybe won't go into details with right here, but I can just flash them at the end. Okay, so now I've kind of given you the hand-wavy picture of, oh, you have these kind of gap boundaries, and you can use them to find anomalies of these fusion category symmetries. But maybe now I'll put those on a bit more concrete footing and tell you more about what are data that specifies these topological orders, specifically the Drinfeld center of a fusion category, and then what defines a Lagrangian algebra. So, oops. So let's talk a bit about 2 plus 1D topological order with an eye towards Drinfeld centers of fusion categories. These are specified by also a set of data. So you have a set of simple objects. Again, whenever you take the Drinfeld center of a fusion category, these simple objects are related to, but they're not they're not the simple objects of your original fusion category. And again, you have fusion rules. So these are given by a set of fusion coefficients, which again define for you the quantum dimension, and you also have the total quantum dimension, which is going to be square root of sum of dA squared. And then you also have F symbol, F and R symbols. And I'm going to do a F tilde here because I'm discussing fusion categories and also their Drinfeld centers, and the F symbol of the center is not the F symbol of the fusion category. And so I'm going to put this F tilde here. So the R symbol, what it does is, so the F symbol again specifies the fusion, the R symbol specifies the braiding. So this is going to be ABC, C, this is ABC. And the reason why I'm telling you about this R symbol is because it will be useful for obtaining the S and T matrices. So for example, you can get the topological spin, which is a property that you can associate with each of the anyons from the R symbol. So this is just going to be sum over C, DC, D, A, R, A, A, C. And you can also get this relation, which you can derive. Theta C over theta A, theta B. So you can use this R symbol to define your S and T modular S and T matrices. So for example, SAB is defined in the following way. This is going to be theta C, theta A, theta B, DC. So of course you could write this in terms of R symbols if you wanted to. And then TAB is theta A, delta AB. The reason why I'm introducing these S and T matrices is because they give you a simple, necessary, but not sufficient condition on Lagrangian algebras, but which I will mention in a sec. Okay, so now you have this kind of topological order that can describe, say, the Drinfeld center of a fusion category. And now let's talk about Lagrangian algebras. So these are, as I mentioned, these are kind of composite, non-simple objects that satisfy this kind of Lagrangian condition. So it's maximal if it satisfies this. This NA is an integer. So this is called the multiplicity. Oops, that's the T. The idea is basically these are the anyons that can end at the boundary, and the multiplicity tells you how many different ways in which you can annihilate this anyon at the boundary. And so this is going to be some integer because it counts the number of ways you can annihilate the anyon at the boundary. It's also, so NA is dimension of a vector space, VA. This is the boundary condensation space. So this is the boundary condensation space. So you have this object and you need additional piece of data. You need an M, something that I'm going to call an M symbol that takes you, that is a map from L times L to L. And it basically tells you how your anyons can end at the boundary. So if I have this boundary, which is blue, and I have anyon lines that are in my Lagrangian algebra, so you have AB, and then you have these mu and nu, which specify the state in your boundary condensation space, then this is going to be equal to sum over C lambda, ABC, mu nu lambda. And then again, you have your boundary here, and you have your anyons, but they have fused already into C, A, B, C. This is going to be lambda. So this is an object that you need in order to specify this gap boundary. And this is not unitary. This process is not unitary. So in particular, what you have is NA and B is less than or equal to sum over C and ABC and C. Right? If it was unitary, then you would have an equal sign. And so these are kind of important properties that we will use when we're looking at to obtain obstructions to gap boundaries, magnetic Lagrangian algebras, because this will constrain what kind of coefficients you can have in your Lagrangian algebra. So the reason why it's complicated to specify a Lagrangian algebra is because you need to have this M symbol satisfy this kind of nonlinear equation. So you have basically MM equals MF. What that will look like is something like this. MF equals MM. So you needed to play well with your F symbol, and you need to find an M symbol that satisfies this nonlinear equation. And that's very difficult. But as I mentioned, oh, this should be your F tilde because it's in your Drinfeld center. But as I mentioned, there are already obstructions you can compute without finding this M symbol. But because you need this M symbol in order to define your Lagrangian algebra, if you don't find it, then at the end of the day, you only have a necessary but not sufficient condition for your fusion category to symmetry to be anomaly-free. if you want it to be sufficient, you need to find the M symbol. And so, okay, so another thing you can show is that the M symbol needs to play well with braiding. So for example, if you have this boundary and you braid your objects, so this is A, B, and this is again, going to be nu mu. This is going to be equal to R. Oops, it shouldn't really make a difference whether you braid them or not once they are once they've been absorbed into the boundary. This is again u nu. And so this condition means basically that M A B A C of nu mu lambda R A B C equals M A B C mu nu lambda. And then it follows from this requirement that R A B C R B A C equals 1 if A, B, C are all in your Lagrangian algebra. You can just solve for R, A, B, C and then swap A, B and then show that this must be equal to 1. So that means that if you have two anyons that are both in your Lagrangian algebra, then in all of the fusion channels that are also in the Lagrangian algebra, they must braid trivially. So this is another thing that we can use if we want to check that our Lagrangian algebra is valid. And as I mentioned, if you make a vector with all these coefficients, then what you can show is that Sn equals Tn equals n. So this vector is an eigenvector of your S and T matrices with eigenvalue 1. So that's another easy condition that you can check for your Lagrangian algebra without solving for these nonlinear equations. Let's go through some examples of Lagrangian algebras. So as I mentioned for Ising, which is also equal to, this is Tambara-Yamagami Z2 pi epsilon. Then for this topological order, because Ising is already braided, this will give you Ising stacked with Ising bar, doubled Ising. And this is anomalous. And the reason why this is anomalous is the only Lagrangian algebra of this topological order is the electric one. There's no other Lagrangian algebra. In particular, there's no magnetic Lagrangian algebra. So that's why it's anomalous. Oops. And then another example is fib. So if you take the Fibonacci fusion category, that's also braided. So that will give you fib times fib bar. And again, the only Lagrangian algebra is the electric one, which is 1 plus tau tau bar, where tau is your Fibonacci anyon. So this is a topological order with 4 anyons, 1 tau, 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 tau bar. And this is the only Lagrangian algebra, and so it's anomalous because there's no magnetic Lagrangian algebra. And then another example of a Lagrangian algebra is when you have the center of vec G with some cocycle, and this will be some Digraph-Witten theory. So it's a Digraph-Witten theory. And then you always have an electric Lagrangian algebra, which basically takes something of this form, dA A. This is the dimensions of the erupts of G. And these are anyons that are associated with the erupts of G. So this always exists as a Lagrangian algebra. If this omega is trivial, then you also have a magnetic Lagrangian algebra. Okay, so these are some examples. These are both anomalous, but then there are also fusion categories, symmetries that are not anomalous. And those are, some of them are found in these Tambara-Yamagami fusion categories. Yes.
Question. Let me just make sure I follow. There's a comment about this M symbol that you say that there's some condition that may lead to non-unitary. When you say non-unitary, like this NA and B is smaller or equal to summation of this fusion MBC, SC. When you say non-unitary, do you mean only for smaller, or smaller will be non-unitary?
Yes,
Okay. And
because it doesn't map you from like the same dimensional vector space to a same dimensional vector space. Yeah.
But you can you can still span the vector space by this formula. You said the dimension does not match, or I'm not sure I follow, because the
So
quality on the top you can still span, but okay.
yeah, so this is a funny property of the Lagrangian algebra, that this doesn't need to be unitary. So an example where this is violated is in the double Fibonacci, right? Because you have L E is 1 plus tau tau bar. And then the n of tau tau bar is equal to 1. And then you have tau tau bar. And then you have tau tau bar times tau tau bar is 1 plus tau bar. And this is equal to 1 plus tau bar plus tau tau bar. And so now you have 1 times 1, because the n tau tau bar is 1, so 1 times 1 is less than or equal to, now this will give you 1, and this will give you 1, right? So less than or equal to 2.
I see.
Yeah, so you can have this condition, and this will put kind of tight constraints on the multiplicities in your Lagrangian algebra. It's kind of non-intuitive, but like it kind of arises from the fact that you can have two objects fused into something that's also not in your fusion category, or not in your Lagrangian algebra, so then it becomes confined.
Let me make sure. So how do you determine the M symbol then? Is that constrained by F? The N, yeah, there's such a condition, but you can already solve M from here.
It's very difficult to solve for M, and I actually don't solve for M in any of the examples that I use. I just use this condition and this condition to rule out the possibility of a magnetic Lagrangian algebra. But if I were really to like try to confirm that my the Lagrangian algebras are magnetic, then I would have to show that such an M exists. Yeah.
And M somehow is also related to the fusion rule in some way, right?
Yes, because it has to satisfy this equation with this F tilde, which comes from the fusion in your Drinfeld center, which comes from the fusion in your fusion category.
Okay. Is M solvable from a complete set of conditions that you know, or is actually just maybe do we know the complete constraint for M in order to solve it? Like,
well, this is a nonlinear equation, so in general, like it's not straightforward to just solve for it.
Okay. All right. Okay.
Yeah.
Thanks.
Yeah, so that's why it's hard. But
sorry, let me just have some simple question. When you write tau tau bar times tau tau bar in the top, the example you try to explain earlier, what's the first equality here?
Oh, this is just saying that tau tau bar times tau tau bar. Well, you can just do tau tau times tau bar. And so tau tau is 1 plus tau, and tau bar is 1 plus tau bar.
Thanks. Thank you.
Yes. Okay.
Sorry. I just want to make sure, is the nonlinear equation you wrote above the only equation that M should satisfy? I think this is Juven's question.
Oh, yeah, so it also has to satisfy this equation.
I see.
Oh yeah, sure.
So
But
these are your two constraints.
I wonder whether these are sufficient, or because sometimes we can write condition, but we don't know whether it's enough to give a solution. Right? So I just wonder whether it's sufficient enough to solve the. I don't know. I mean, do you know that? Do you know it's sufficient?
Well, I mean, given any R symbol and F symbol, there might not be any solution for M.
Right, but
then your Lagrangian algebra would be ruled out if you can't find a solution. But it's not obvious to show like, oh, there doesn't exist a solution for M, I think.
Okay. But you think these are enough complete constraint, right? You don't mean it's constraint. I think that's what I want.
Yeah, so that is given by some papers by like, so the mathematical definition of a Lagrangian algebra, this is kind of a physicist's perspective of Lagrangian algebra. And so you can show that it's equal to the mathematical definition of Lagrangian algebra that was shown in Kong et al. In a couple of papers like Hamiltonians with gap boundaries, with Zheng Wang and Meng Chen.
Okay.
So that show that this is equivalent to the definition of Lagrangian algebra in the math literature.
Okay, thank you.
Okay. Let me just and the remainder, because I guess it's already quite a long time.
And take your time. You need till 12, like another 40 minutes is fine. Whatever time you want. Take your time.
Well, let me just quickly define what I mean by Tambara-Yamagami fusion category, so we can see kind of the non-trivial examples where we're actually working with fusion categories and we find anomalies. So we're gonna look at Tambara-Yamagami fusion categories. And let me first define these fusion categories. So to define the fusion category, I need to tell you about the simple objects, the fusion rules, and the F symbol. So let's define T, Y, G, chi, epsilon. And so this was studied in Tambara and Yamagami, 1998. And this was actually solved for from the Fiberfunctor perspective from Tambara-Yamagami in 2000. Or just a Tambara. Okay. So the simple objects are going to be elements of your abelian group. So G is some abelian group. We're going to focus on Zn quasi n, but you can do any abelian group. And there's also a duality object. So those are the objects in your fusion category. And the fusion rules are, well, the abelian objects have your usual abelian fusion. But in addition to that, you have this. So the sigma, the duality object, absorbs all of the group elements. And sigma times sigma is going to be a sum over the group elements. So this is a sum over all G and G. These are our fusion rules. And now we have F symbol. So a lot of the F symbols are trivial. So a lot of them is just equal to 1. But these are going to be the non-trivial ones. The non-trivial ones are given by F, G, sigma H, sigma equals F sigma G sigma H sigma. And this is given by your symmetric bicharacter. You can show that this has to be the case by plugging this into the pentagon equation and solving the pentagon equation. And you'll show that this chi has to obey certain properties. But let me just first write down the other F symbols. Oops. F sigma G H. Oh no, my pen might be running out of, okay, should be okay. Square root of G, chi G H inverse. And so this chi is our Frobenius-Schur indicator. And this this epsilon is our Frobenius-Schur indicator, and this chi GH is a symmetric bicharacter. So if you plug it into the pentagon equation, you'll see that it obeys these properties. HG chi GH equals chi G K chi H K. Oh no, okay. And then chi G HK equals chi G H chi GK. And it takes you from two group elements to a U1 phase. And so if we are looking specifically at Zn quasi n, so for Zn quasi n, these properties here mean that all we need to specify are the following. So we can specify x equals chi 1 0 1 0. So this is Zn quasi n. So the one is saying the non-trivial element of the first generator. Y equals chi of 0, 1, 0, 1. And then we have Z equals chi of 1, 0, 0, 1. And we only need to specify these three elements because any chi of any other element can be obtained from these relations on these particular choices. So I should mention that not all choices of X, Y, and Z are valid because you also need your F symbol to be unitary. But two choices of this bicharacter that are valid are the diagonal bicharacter, which I will is given by this. And the off-diagonal bicharacter, which is given by this. And you can check that both of these give you a unitary F symbol. For Z and quasi-n. So these are the two bicharacters that we're gonna study. And let me tell you, so there are two ways to get the center. So there are two ways, in this case, to get the center Z of T, Y, G, chi, epsilon. One way is by gauging a duality symmetry of G gauge theory. So you start off with some abelian gauge theory, which is specified by this abelian group, and then there's some permutation symmetry. The permutation symmetry is specified by the bicharacter that you choose. So given a bicharacter, that tells you which permutation symmetry you have. And the Frobenius-Schur indicator tells you whether or not you stack with a Z2 SPT before you gauge the Z2 duality symmetry. So one way to get this Drinfeld center is to take an abelian gauge theory with the Z2 duality symmetry that's specified by this bicharacter, and then to gauge that symmetry, and you can gauge it with an SPT or not, and that gives you a choice of Frobenius-Schur indicator. The physical meaning of the Frobenius-Schur indicator is that, like, if you gauge it with the SPT stacked on top, then that will change the topological spins of the duality anyons by a factor of I, which comes from the fact that the vortices of the Z2 SPT are semions. The second option is to directly compute the Drinfeld center from the string net construction. And so that is in 11 and 1, 2005. And then also Lin, Levin, Bernal, 2021. So this method is convenient because it allows you to get the anion content of the Drinfeld center pretty easily. But if you want to compute more complicated things like the topological spins of the anions, then it's kind of hard either way you go about it. So I actually use the string net construction for that. Okay, so there are kind of two levels of obstructions. One of them is very easy, and the other is very hard, or it's not that hard, but it's harder. Two obstructions. One is the existence of a duality invariant Lagrangian subgroup of the G gauge theory. So this only depends on the bicharacter because the duality symmetry is only specified by the bicharacter. So if you have a G gauge theory, so the G is specified by the abelian group for which you're taking the Tambara-Yamagami fusion category. So if you have a G gauge theory that does not have any duality invariant Lagrangian subgroups, so these are Lagrangian subgroups, which if you apply the duality symmetry, it maps the subgroup back to itself. So if there are no duality invariant Lagrangian subgroups, then that means that if you look at the SET, like before you gauge the duality symmetry, then the SET can't even have a gap boundary that respects the Z2 permutation symmetry. What that also means is that there's no 1 + 1D theory that has of this there's no 1 plus 1D G SPT that's even invariant under the gauging procedure that's not on site. If you take the gauged theory, then that means that any Lagrangian subgroup of the gauged theory spontaneously breaks a subgroup of the abelian G part of the fusion category, let alone the other, like just the categorical non-invertible part. Basically, this is just an easier anomaly that you can compute. And this has been studied in depth and from the procedure of explicit gauging. So what you can do is you can look at all the SPTs of a G symmetry and see if you can have any SPT that comes back to itself under gauging. If you don't, then you don't have a duality invariant Lagrangian subgroup. And I'll go through some examples. So, okay, so when this is this obstruction fails, so there does exist a duality invariant Lagrangian subgroup of the original G gauge theory, then you need to do the harder one where you look at if there exists a Lagrangian magnetic Lagrangian algebra of center of the. Okay, and this part depends also on the Frobenius-Schur indicator. So the Frobenius-Schur indicator doesn't play a role in this first obstruction. Okay, let's go through some examples so that we can work this, at least this easy obstruction out. So the diagonal bicharacter corresponds to the following permutation symmetry. It's when you take E1, you take the permutation symmetry of E1 with M1 and E2 with M2. Remember that we're looking at Zn cross Zn. So we have some Zn cross Zn gauge theory. Zn cross Zn gauge theory is the anyons are generated by E1, E2, M1, M2. And there's a duality symmetry which permutes E1, M1, and E2 and M2. That's the diagonal duality symmetry. The off-diagonal duality symmetry is when you permute E1 with M2 and E2 with M1. This is another valid Z2 duality symmetry of your Zn cross Zn gauge theory. It's just a different duality symmetry. And now let's look at when there exists a duality invariant Lagrangian subgroup. One can show that all of the magnetic Lagrangian subgroups take the following form. They're the anyons generated by one M1 E2 to the P, M2 E1 to the minus P. So in our Z2 cross Z2 case, right, we had P equals 1. So we generated our anyons by M1 E2 and M2 E1. So this is a generalization to any N. Any magnetic Lagrangian subgroup. So, okay, and if you take P equals 0, then you just get your other. So in Z2 cross Z2, we had two magnetic Lagrangian subgroups. One of them corresponded to P equals 1, and the other corresponded to P equals 0. And in the diagonal duality, we need this to be invariant under the diagonal duality, right? So if we take M1 E2 to the P, the diagonal duality will map that to E1 M2 to the P. And we need E1 M2 to the P to be generated by these anyons. So in particular, we have E1 M2 to the P to the minus P is equal to E1 to the minus P, M2 to the minus P squared. And this object must match with this object here because it's E1 to the minus P. So that means that you have to have a P such that P squared equals minus 1 mod N. So that means that if you're looking at Zn cross Zn Tambara-Yamagami fusion categories, they can only be anomaly-free if you're choosing this diagonal bicharacter, if minus 1 is a quadratic residue mod N. For other choices of N, they have to be anomalous. Okay. The off-diagonal bicharacter, you have M1 E2 to the P, that maps under this off-diagonal duality to E2 M1 to the P. And now what we have is we have E2 M1 to the P equals E2 to the P M1 to P squared. And so now we have to identify this guy with this guy here because they're both E2 to the P. So now what we have is P squared equals 1 mod N. but you can always choose p equals 1. So for any n, you can always choose p equals 1, which satisfies 1 squared equals 1 mod n. So that means that if you have the off-diagonal bicharacter, you can have any n. Okay, so from these two results, now we know all we have to consider is the diagonal bicharacter when -1 is a quadratic residue mod n, and the off-diagonal bicharacter for any n. Okay, that's a easy obstruction to compute. Now let me just quickly tell you the anion content of this center. If you use the, so what you can show is the anion content. There are two G abelian anions, which I labeled by these AGR. So G gives you G, and then R can be plus or minus 1. And then there's G choose 2, dimension 2 anions. These kind of come from the anions of orbit 2 under the duality symmetry, and I'll call them BGH is BHG. So there are G choose 2 of them, where G is not equal to H. And then there are duality anions. So there are 2G dimension square root of G duality anions. So in doubled Ising, right, there are 2 duality anions, and then there's one anion of dimension 2, which is sigma bar. And then there's also 2G abelian anions, 1 psi and psi bar, and psi bar. So this is the anion content, and I'm going to label these by CGR. And now let's look at the topological spins of these duality anions. I've computed the topological spins of these duality anions are given by this. This is a summary. What you can see here is that if you choose the -1 Frobenius-Schur indicator and n equals 2, there are no bosonic anions of this type. And similarly, for Frobenius-Schur indicators -1 and n is greater than 2 and n is odd for both the diagonal and off-diagonal bicharacter. The star just means that we're only considering n for which -1 is a quadratic residue mod n. So this means that for these 3 classes, the fusion category symmetry is anomalous. And the reason is, what you can show is that if you want to construct a Lagrangian algebra that intersects trivially with the electric one, you need at least one of these guys to be bosonic. But when you compute the topological spins, there are no bosons. There are no bosonic duality anions. So that means that this fusion, there aren't enough bosons to construct this magnetic Lagrangian algebra. So they're anomalous. The details are kind of tricky, so I won't go through them, but maybe I'll end with the outlook and kind of a lot of the remaining questions that I think are interesting. So let's talk about outlook. So first, I think it would be interesting, or like a long-standing problem is mapping directly between module categories and Lagrangian algebra. They all define gap boundaries of a topological order. So Fiberfunctor is a module category with a single simple object. So a particular aspect of this mapping is between Fiberfunctors and magnetic Lagrangian algebras. And one kind of interesting thing is it's very easy to derive from the Fiberfunctor perspective that fusion category symmetry can only be anomaly-free if all of the objects in your fusion category have integer quantum dimension. And I can prove that pretty easily, but maybe I won't go through that here. But that's very non-obvious from the Lagrangian algebra perspective. Why does the objects have to have integer quantum dimension in order for there to exist a magnetic Lagrangian algebra? So that's one outstanding question, how to map between the data that defines these two. and for general fusion categories. Another is 1 plus 1D lattice models. Given a Lagrangian algebra. So given a Lagrangian algebra that should specify 1 plus 1D lattice model, for example, if you are given a magnetic Lagrangian algebra that should specify 1 plus 1D SPT of the fusion category symmetry, but it's not obvious how to actually really construct that concrete lattice model. And this is also related to how to construct string net models with boundaries and how to construct models for anion condensation for non-abelian topological orders. So that's still an open question. Another question is the phase diagrams of systems with these phases. If you have multiple SPTs, how do you tune relevant operators to get between these SPTs? Another question is more general fusion categories. I've studied Tambara-Yamagami ones, but it would be interesting to study other kinds of fusion categories that have integer quantum dimensions. And then another really interesting question is the generalization of the story to higher dimensions. So this has been recently explored in Choi et al. 2022 and Akta et al. 2022. This is particularly interesting actually in 3+1 dimensions, categorical symmetries in 3+1 dimensions. Basically because you can have one form SPTs that are invariant under gauging. So then you'll be looking at the boundaries of 4+1D topological orders that contain loops. And so finally, another question is what are the different kinds of anomalies? So in abelian groups, we know there's like type 1, type 2, type 3. But here we don't really have an understanding of the structure of the different kinds of anomalies. These are related to linking invariants, different kinds of linking invariants in the bulk topological order in the Drinfeld center. And it's related to the story in this recent paper. 2023. And then another final question that I'm going to put out here is how to extract the F symbol from the topological operators. So in the group-like case, this was given in Kyle's paper with Michael Levin and also in Elson-Nyack, but the generalization of that method to fusion category symmetries and topological operators that have non-invertible fusion is not obvious. So that's another remaining question. So with all that said, yeah, I'm happy to take additional questions.
Thank you very much, Carolyn, for the great talk. Thank you. Question from the audience. Please feel free to ask questions or comments. Actually, yeah, I don't know whether people have questions, but I have many. Let me think about this. Do we consider here is, should we call one category, and this is zero symmetry? Is that correct?
Yeah, so if you look at, so this would be indeed, there's only the morphisms, one morphisms, but then if you look at higher dimensions, then it would be a higher category.
But so far it's one category, zero symmetry. Is it correct? Zero symmetry. The charged object is zero dimension.
Mm-hmm.
Okay.
It's a zero form global symmetry, yes.
Actually, I still want to understand better this symmetry, spontaneous symmetry breaking picture you try to kind of point out. Not sure I exactly get the point. here you try to provide a way to check whether this theory in 1 plus 1D has anomaly or not, right?
Mm-hmm.
And then if it has anomaly, it cannot be trivially gapped,
Mm-hmm.
right? And spontaneous symmetry breaking can happen with or without anomaly, I suppose, right?
Mm-hmm.
So how is spontaneous symmetry breaking here? Maybe help us to understand something.
Yeah, so the idea is, as you said, spontaneous symmetry breaking can happen with or without anomaly. But if you have an anomaly, then you can't get a phase that doesn't have any spontaneous symmetry breaking and is gapped, right? And so then the idea is, if it's anomaly free, then you can have the second scenario. So we're using the presence of this trivially gapped phase to identify anomaly free condition.
Right. But yes, but sorry, but spontaneous symmetry breaking can happen for some gap phase. And because this is 1 plus 1D, so you cannot have a symmetric gap phase that has anomaly, is it? That's also okay. I see. So maybe some of the condition of this picture maybe limited to 1 plus 1D or
Yeah, so in higher dimensions, for example, what you'll want is because in higher dimensions, the anomaly can be cured by, say, topological order, right, of a zero form symmetry. But then what you'll want is this unique ground state on any manifold, right? So in 1 plus 1D, you have a trivial gaps theory that has a unique ground state on any manifold. So for example, in 2 plus 1D, you also want this system that has a unique state on any manifold, and that will tell you whether or not your symmetry is anomalous or anomaly-free.
right. Yes.
So as you said, the spontaneous symmetry breaking, I mean, unless you consider higher form symmetries as well, but of the zero form symmetry that may be anomalous, it could be cured by topological order.
Yes. But also the I think here you try to say these are the spontaneous breaking of some zero form magnetic symmetry, right? Here it seems like what is drawn is the charge operator, which is the electric lines or electric. These are the charge operator of which is electric. Maybe for the rhetorical picture it's more clear, but I'm not sure whether I really get the picture for generic case. I think. Yeah, so let me just try to clarify, because for Z2 torical or Z2 gauge theory, we do have the charge operator, which is electric. For the charge operator for the magnetic symmetry, let's say for 2 plus 1D bulk, the magnetic symmetry is one form magnetic symmetry, and the charge operator is the electric line, Wilson line. But then I'm not sure what I get for other cases, like beyond torical. Can I always identify the charge operator? If that's an electric line, is that the charge object will be some magnetic object? I think I don't. Yeah, maybe this may be subtle, but
yeah. So it's a bit tricky in other like non-abelian topological orders. What you want to think of is not the anyons, right? Because the bulk anyons are different from the boundary excitations.
yes.
And so what you want to do is you want to specify the gap boundary, and then that will give you a zero form symmetry that comes from the low energy excitations at the gap boundary. Those are not in general in one-to-one correspondence with the bulk anyons, right? So I think that's a subtlety. So whenever you define a gap boundary, that will define some low energy excitations, which will define for you a symmetry, zero form symmetry once you squeeze the system to 1 plus 1Ds. Yeah.
Yes, but when you squeeze the system, actually, I also want to ask, do you try to reduce the dimension of the charge object or charge operator in this picture? It seems like you are saying the charge objects.
It becomes a zero form. Because it's a zero form symmetry.
In that case, the charge operator will still be one-dimensional for that symmetry.
No, the charge operators are zero-dimensional because this is zero-form symmetry in 1 + 1D.
The charged object will be zero dimension, yes, but charge operator in 1 + 1D will still be one-dimensional.
It's zero because this width is very small, so it's like a zero-dimensional operator, right? Another way to think about it is if you instead of thinking, if you are uncomfortable with this picture, you can instead think about condensing in the bulk as well as on the boundary. So if you condense this Lagrangian algebra in the bulk, then you'll get a trivial theory in the boundary, and you'll be left with a 1 + 1D theory, which can have a symmetry that's zero form and spontaneously broken. So either perspective is okay.
Maybe repeat again, sorry.
So another way to think about this is if you have the 2 + 1D topological order, and you condense the anyons in the bulk and on the boundary. So if you condense them in the bulk, you'll get a trivial theory. So then you can define the edge theory is just a 1 + 1D theory that can be defined for you a symmetry that's spontaneously broken. But yeah, so either perspective is okay.
Yeah, but yeah, I guess I think in 1 + 1D, the charge object, if these are zero form symmetry, I think the charge operator still be one dimension, and anyway, the way I yeah, anyway, I guess maybe I should ask privately. This requires to draw a picture maybe in a more evolved way, so let's not doing this here. Any question, comments from the audience?
I think there was a question, but I can't.
Oh, I'm sorry. I wanted to ask a question just shortly. It may sound a bit naive, but can this model be applied to condensed matter applications? Does it have such applications? Because of course it's like related to bosons.
Yeah, so this has applications. For example, if you're looking at these anion chains in 1 + 1D, that's a natural setting in which you have a fusion category symmetry. And if the fusion category symmetry is anomaly-free, then there should be some parameters that you can tune to get into a symmetric gap phase. And so that would be a natural setting in which you can even look at the entire phase diagrams of these kind of systems and how to probe into different SPTs. So for example, people have studied a lot this Fibonacci chain, this golden chain, but then you can do that for any kind of fusion category symmetry.
Yeah, this makes sense, honestly. Thank you, actually. Thank you so much.
Okay, any more question, comments? If not, we should thank Carolyn. Thank you very much. Thanks. Thank you.